Okay, so I feel like last week was a little bit too unstructured. So I write down all the things in a more exact sense, and then hopefully if you already it will make more sense, and then you can refer back. So this part was about set, which I talked about previously, and then we have the set builder notation. You can I will not like teach this again, and then so you can just like look at all the things whether you are sure of it or not. So membership, inclusion, and then intersection, union. There's one thing that I didn't mention last week, and I would like to mention now, which is this cardinality thing, which is basically the cardinality of the set is basically the number of distinct elements in the set. So example would be this. And then in set, we don't care about repetition, just like in programming language. Then divisor and prime are all the same. This one is fine. Okay. So now today I'm going to talk about computational complexity. So just want to know how many of you all is like completely new on this topic, like zero background on this. Okay. Okay, then I will try and make it a little easier to understand. Actually, I made this lecture notes, not lecture notes, this note quite self-contained, so I hope it's fine. Okay, so the thing about computational complexity is we want to calculate how quickly the algorithm runs. In particular, we know that brute force is slow and sorting is fast, but how do we precisely define what is fast and what is slow, right? And furthermore, sometimes we have different computers. Like if you use like a supercomputer, then it could run your algorithm faster. Or if you use a regular computer, something like a RSA, or even like something very, very slow, like a Raspberry Pi, then they could run at a slower speed. But then, so different running speed on different CPU power. So this will make it very hard to define how quickly an algorithm runs. And it's very hard to do it in terms of time because yeah, technology is also advancing. So computers should be able to run things faster. But regardless of the computer speed, we're still interested in knowing the general trend on how slow this algorithm is. So here I start by introducing this new notion, which is called instruction count. So a very naive way to count how fast an algorithm runs is to count the number of instructions. So like for example, we define, okay, so here we define Fn as the number of instructions by the algorithm A, where n is the input. So let's see this example, okay? So we have, this is a Python code, and then the first basically takes in input n, and then for loop and print hellos. So how many instructions are being run by this program? Perhaps we can write it as Fn is equals to n plus 1. Why? Because you can, this is essentially just like one instruction. But of course, you know, we have we have converted the input into integer. You can also regard this as two instructions, right? Because you are writing on the same line. But let's just assume that we are just doing online now. And then now we have the for loop, right? So for this for loop, you're looping from 1 to n, and then for each loop you do print hello. Intuitively, you can think of it like this has print hello has been this instruction, this line has been done for n times. That's why the final instruction count will be Fn is equals to n plus 1. But we know that underlying the for loop, right, we have the variable I, and this variable I is always changing in every loop. So behind the implementation of the programming language, I is somewhat replaced by a new number, right? And then should we even count this new instruction inside? So it kind of makes it quite difficult to explicitly write down the number of instructions that is actually being written down. But if we just look at number of lines, then maybe you can just write Fn is equals to n plus 1. So is this okay? Now let's look at another example. So we have this code, which is that the first line takes in the input n, And then if n modulo 2 is equals to 0, then I do the for loop. Otherwise, I just print 1 and then I end the output. So here it's even harder to define things now, because if n modulo 2, which is the first part, then we have to do a looping. And if n if 2 does not divide n, oh sorry, this should be n, then we just have 3 instructions, because if we consider this as 1 instruction, the for loop as 1 instructions, and this one as 1 instructions, then we only have 3 instructions, right? So it becomes like a case function already, right? You have different case, different inputs, and different case give different instructions count, and it makes it even harder to write this down explicitly. So here we can look at another example, which is a double for loop. We have a nested for loop. So here we take in an instruction n. We have an instruction to take in an input n, and then we do a nested for loop, which is I repeat this part for n times. So you want to calculate. Okay, so for example, this is if let's say this run for 1 times and this, right? So how many times is this instruction being run, and how many times is this instruction being run? Let me use another color. Like you can write down your answers in the chat or something. Like how many times has this instruction being run? The print hello, and how many times the print world is being run? Any guesses? Okay, so let's make it in terms of n, right? In terms of n. Right. N square is a very good guess, right? Why? Because for j in range n means that this part will repeat for n times, right? And then this, and we got another for loop inside, and so this part will repeat for another n times. So intuitively, this will somehow give like n square times of. So if I run this code, if I put 10 as my input, then I will get 100 lines of print hello. I will run print hello for 100 times, which means that the final output screen that I get will have hello for 100 times. 100 times. And you can sort of verify it yourself, but yeah, but that's the how nested for loop works. And then for the second part, you realize that this print world is outside the loop, right? It is not inside the nested for loop. So this should be run for, oops, sorry. So this should be run for n times. So in total, if we count the total number of lines, instructions that is being run, maybe we can write this function down, right? So the instruction count for this algorithm Fn is equal to n squared plus n plus 1. Means that if I put if my input is 10, if n is 10, then Fn will become 100 squared plus 10 plus 1. So this will be, we will sort of expect the CPU, the processor, to run this line, how many lines of instructions, like this will be the number of lines of instruction that it has run. Okay, any questions so far? Okay, let's look at another more complicated example. So instead of like doing loop from 0 to n, which is what we are doing previously, now we are doing from I to n. So when we are doing for I to n, then this becomes much more complicated to analyze, right? Because if okay, let's say if I is equals to n minus 1, then probably this one will not be will only be run for once, right? And then if I is equals to n minus 2, then we have range from n minus 2 to n, then this will be run for 2 times. And if I is equals to n minus 3, n minus 3, then this line will be run for 3 times. So the total number of instructions that we get is somewhat more complicated. Like this print hello line will run for n plus n minus 1 plus n minus 2 plus n minus 3 all the way until 1. And then this one comes from this part. So this first line corresponds to the one here. And then this corresponds to the print hello. So this is the print hello, the number of times that print hello will be run. Understand so far? Any questions? I don't want to rush this. Okay. Right. So how do we get this to this? This is some mathematics, but basically you are trying to find summation from 1 to n, where this is I. So this will become n times n minus n plus 1 times 2. This is just formula, and I will not talk too much about this. So yeah, so we got a more complicated function right now. Okay, I want to check on Yi Hang. Can you understand this, because you have no background on this?
Trying.
Oh, got any questions?
The last one that you convert it to divide by 2, that one is just formula, as you said.
Yeah, that is just formula. Important part is you understand this. If you understand why is n plus n minus 1 all the way until 1, then that is enough.
Okay, yeah. That
okay, so you can understand that part, right?
Mm.
Okay, good, nice. So okay, you see that. Okay, so what we see that is for different functions, we need to, if you want to count the number of instructions, we have to do it manually. We don't really have an automated way to do it. And then it also depends on a lot of cases. So now let's look at okay, so now let's look at this first. Okay, so we have n is input, and then for I in range 1000, and then I print hello. So this will naively just be 1000 plus 1, and this will just be 1001. So I believe this is okay for you all now. Okay, so now let's look at a more complicated algorithm. Yeah, so this is 1000 plus 1. Which one is plus 10 in the middle? Sorry. You mean the previous or this one? I think it was a typo. Is it on this question? Can you confirm? Okay, yeah. So this is 1 plus 1000. Okay. Right. So now we have know how to calculate. Wait. What? Sorry. What question do you have? Oh, the second question. Okay. Which one? This one? Okay, let me explain it again. I'll clean out this mess. Okay, so first, do you understand this part? Why is it fn is equals to n squared plus n plus 1? Okay, then maybe I will try and explain this function. Why do we even get this? So firstly, the 1 here is correspond to this. Okay, so this 1 here is correspond to this instruction, and then the print word here is correspond to n. Sorry, my drawing is not very good. Okay, yeah, and then the n square is correspond to this. So why is this n square? Is because we are doing a nested loop. So when we are doing a loop, right, we basically say that this part repeat for n times. So the block repeat for n times. And then inside the internal block, we repeat for n times again. So this will become n times, which is why we get n squared. And then you see the world outside, right? So the world is not inside the nested loop. So this will correspond to n. Okay. So why do we have the trend just now is that I was giving an example. So like if we have f10, f10 is equal to f10 to the 10 to the power of 10, and then power of 2, sorry, plus 1. So what this basically says is that we can expect we get hello for 10 times, and we get world, sorry, for 100 times, we get world for 10 times if n is equal to 10. Okay. Right. Okay, good. So yeah. Right. So I suppose then I will just like talk about this again, right? So why do we even have this n plus n minus 1 and so on is because of this I here, and then the I changes every time that when during the loop. So when I is equals to 0, then this part will run for n times. When I is equals to 1, then this part will run for n minus 1 times, because the loop count is decreased, the number of iterations is decreased. So we get this notation, and then why this become this is a formula, so we don't care about that. Okay, so now let's move on to this part. So how do we analyze like a simple algorithm like a bubble sort? Okay, so I just want to confirm if everyone knows about bubble sort and how bubble sort works. If you don't know, then I'll show an example. So can I confirm if everyone knows this? Okay, 5, 4, 3. Okay, need an example. Okay, sure. Right. So what bubble sort does is that we have bubble sort is a very simple way to do it. So basically, let's say if I have 4, 2, 3, 1. So in the first loop, I will look at this element 4. Okay, so I check, is 4 larger than 2? 4 is larger than 2, right? Then I swap. I swap to become 2, 4, 3, 1. Then I continue looking at 4. Is 4 larger than 3? 4 is larger than 3. Yes, so I swap. So this becomes 2, 3, 4, 1. And then I look at this again. Is 4 larger than 1? Yes. So I swap. So this becomes 2, 3, 1, 4. I do have space. Okay, 2, 3, 1, 4. Then notice that every iteration, we always have the largest element at the final position, right? Because if you think about it, what I'm doing is that if I see this element is larger than the element, then I swap it. So after every iteration, the last few elements will always be sorted. So this part will always be sorted. You can check it yourself, but what happens is that basically, yeah. So this is the algorithm here. The algorithm here is the bubble sort algorithm. So you see that I do n times loop, and then for each loop I iterate from 0 to n minus 1, n minus I minus 1, which is basically I iterate until this part. So like for example, in the first iteration, I will iterate until here. The second iteration, I will okay. Okay. So let's say if I have 4 elements here. So at the first loop, right, then I will iterate until final, and then the second loop I will iterate until here, and then the third I will just iterate until this, and then finally I just iterate until here. So basically, yeah, you see that it's just that if the current element is larger than the next element, then I swap it. So this is the usual way to write swapping in Python. And then I write swap is equal to true. If it's not swap, right, then means if this is if sort is set to false, means that this part of the algorithm is not run at all. So means that the array is already sorted. So I will just break. However, if there is some swap going on, then it means that it could be possible that the array is still not sorted yet. So I still need to continue going this thing. Okay. Can understand? So why is it called bubble sort? Is because of the intuition that the largest bubble will go to the highest place, right? So you have this. So this is the reason why it is called bubble sort, because the larger bubble will float to a higher place. Okay, Yihan, can you get it? Or do you need more examples? I can show you a video if you want. I in range. Okay, so I in range n means I will go from 0 to n minus 1. So in each loop, right? So one loop will I will become 0, the next loop I will become 1, and so on until n minus 1. So range this until here means j will go from 0 to n minus I minus 1. It can get a little bit confusing because yeah, the last place don't need the sort. Yes, exactly. Okay, I think I should still show the video, because I'm not sure whether you all have seen it before, but it's a very good visualization on how they actually do. Give me a second. Okay, let me share my screen. Okay, yeah, so this is I'm not sure how many of you have seen it, but you can think of it that so the length of this thing is basically the numbers. You can think of the larger number has a higher length. So yeah, you can see that after the sort, right, then the last element will always the last part will always be sorted. Let me just make it quicker. And then at the very last few iterations, then it gets quicker and quicker and quicker and quicker and quicker. But you see that, okay, you see this element right here, right? So this element is very small, and then it has to sort for many times until it can reach this final point. Okay. Right. Okay, I hope that gives a little bit more intuitions on this. Okay, let me share back my screen. Yeah, nice. So now let's try to analyze the runtime of this algorithm. How do we do it? So if we want to actually write down the fx, fn, we need to a lot of cases. Okay, so there are many different type of arrays, and the different arrays will give different runtime. Then explicitly write down fn is extremely difficult, because you have to account for all the case. And yeah, so it becomes much more tedious even for a relatively simple algorithm, because you see this is not like super complicated, it's just a few lines. So that gives us a motivation to introduce asymptotic notation. So it is not always easy to write down the explicit instruction counts of a function. And even if we actually write down, compiler optimization and programming languages could change the number of instructions actually run by the processor. Like for example, the for loop here could be unroll or something like that, or maybe like it could be unoptimized and make it more like make it requires further more instructions and so on. So it is very hard to analyze. Therefore, we simplify our estimation to only look at the general trend. So the keyword here is the general trend. So what do we mean by the general trend? Suppose that we have this function, this instruction count function, 3n squared plus n plus 1. We know that when n gets very large, this first term will dominate the function. Because you can just illustrate this with a very simple example. Let's say if you put like 1000, then this n squared will become 1000 to the power of 2. This will be plus 1000. 3 times 1000 plus 2 plus 1. So you notice that this part is very, very large compared to the other two. That is what we mean by dominate the function. So because we know the largest term will dominate the function and make the rest of the term insignificant in the grand scheme of things, so we can say that the general trend of this function is 3n squared, right? So yeah, it should sort of grow. The number of instructions count should be sort of like around 3n squared. So that's what we're trying to say. However, due to compiler optimization, we can't really find the right constant factor for 3n squared. Basically, this means that 3n squared, although we count the number of lines is 3n squared in Python, maybe when we compile it into machine language, right, it could be 6n squared operations. Like maybe like one loop will have like some add operations and then some jump operations and so on. So that in practice could be much larger than what we thought of or lower than what we thought of. So this 3 and 6 is very hard to actually decide on in the actual application. Therefore, we further simplify our notation approximation to not look at the coefficient. So we only look at the terms. So therefore, what I can say is that the general trend of Fn is only n squared. Because I can't really decide the constant factor. The constant factor could be very large, could be very small. So I don't care so much. I just look at the term. So this term will be n squared. Okay, so far. Before I move on to big O notation, which involves a lot of math, does this make sense? Any questions? Ihan, got any questions? Okay, yeah, that is good. Okay, nice. So, okay. So now we have to introduce something that we often see when we are doing algorithm, which is the big O notation. And we are going to look at this slowly. Okay, so, right. So let's say I have a function Fn, which is my counting function. We use this notation, big O, bracket Fn, to determine the asymptotic approximate upper bound for a function. Here I want to note that asymptotic means towards infinity. You can say that like trend towards infinity. It basically says that if your n is like very, very large, then what is your general trend? Okay, and then we say that Fn is equals to OGN if there exists a number m and n such that for all x larger than n, we have this thing. Okay, this seems very complicated, but it basically says this thing. Okay, so it basically says that let's say if I have my counting function, and then I can write Fn is equals to OGN if this thing holds. Okay, so it's kind of not very easy to understand throughout through the definitions, but let's look at example. Okay, we just look at this example. Firstly, we have 4n squared is equals to 10n squared. Okay, why is this the case? So you see that, okay, now what I'm doing is that I let Fn is equals to 10n squared. And then we can write O Fn is equals to n squared. So remember what I said about general trend just now, which is to ignore all the coefficients and only look at the last term, the largest term, that is basically what big O notation is doing. But to express it mathematically, we have to use a lot of definitions. But basically, that is just what it is doing. So we have yeah. Actually, I think okay. So this part this part is wrong. I shouldn't write it like that. I should write it in other way, which is that I should write it as n square is equals to O10 times n square. Okay. Yeah. The direction is wrong. Sorry. Yep. I should write it like that. This should be the right notation. So in all this should be n square is equals to O10 to the n square. Actually, never mind. Yeah, I think it's the same thing. I mean, yeah, it's the same thing. It's the same thing. Never mind. Never mind. Yeah. You can just use it. Okay, it's fine. It's fine. Right. So, yeah. So what this means is that my fx is, let's say my fx is 10n squared. Then we can write this as on squared, because this is basically the largest term, right? So the largest term is n squared, and then we ignore all the coefficients. So we write this as on squared. Then we look at this example. This is 100n squared. It is, when I write this as this thing, right? It basically means the same thing. Okay, so this is also this. So because I will always ignore all the coefficients. So the coefficients doesn't matter. You just look at the terms. And then another example is here. Okay, so we have this, right? You see, this is a very complicated thing, but we don't care about the coefficients and the lower term. We just look at the final coefficient, which is n squared. Okay, so lastly is for this part. What is 1 billion? So technically 1 billion is not expressed in terms of n. So that basically means that this 1 billion is equals to 1. Because we only takes the largest coefficient, largest term, and ignore all the coefficients. And this we can express this as 10 billion multiplied by x to the power of 0, which is x0, which is 1. Okay, so far is this okay? We don't look at the proof first, but is all this okay? Yeah, ignore coefficients. Ignore coefficients. Okay, and then this definition right here, basically, how do you express ignore coefficients in how do you express ignore coefficient in terms of math? So you use that's why you have this complicated notation. So like for example, let's say if my fx is 3n squared, right? Then if I can set my m to be 10. So if I set my m to be 10, then 10 multiplied by n squared will always be larger than 3n squared. So I express the meaning of ignoring coefficients by letting this m to be any integers that I can choose. So what I say here is that there exists a rational number m. So this basically says that I can have, if you have some coefficient 3, then I can always find a integer that is larger than 3 to become my coefficients, and then these functions will always be larger than that function, than the previous function. So I can always be 1 up higher than you. And with this free choice of m, then that is basically the way that I can express in mathematically ignore coefficients. Okay. And then we also have to take care of the situation where we have, like for example, let's say if Fn is equals to n plus 100, all right, then what happens is that let's say if my Gn is equals to 2n, when I put n is equals to 1, this will become 101. But when I put n is equals to 1 for this will become 2. Then it will not satisfy this condition whether that fx is smaller than or equal to gx, because I already have a 1 that. So like if you look at this graph, right? If you look at the graph, the first graph we will have something like that. So this is fn, which is equals to n plus 10, 100. So this is 100. And then the second graph we have is here. So this is 2n. Gn is equals to 2n. So you realize that at this earlier part, right? This earlier part, Gn is smaller than Fn. But we don't want this to happen, right? So that's why we have this second condition that we only care about large enough n. So we can set an n to be so large that we only want this condition to hold when x is larger than that. So like for example, in this scenario, we can set n to be 1000. So in the case of 1000, G1000 will be 2000 already, and then this will be 1001. So Gn will always be larger than Fn already. That is the way that we use to the ways that we use to express the reasoning of ignoring the smaller terms. Okay, so why do we make things so complicated? So the first part that we have here, okay, let me erase this. So this first condition, this first part is to ignore the coefficient. And then the second part, that n, such that for all n, this only holds. This is to ignore smaller terms. And with these two conditions together, then we have that fx is then we can finally express what we want to say, which is that you only look at the largest term. So that is the finally the thing that we can say. But yeah, it is expressed quite it is quite complicated to look at it that way, but that is the formal definition of Big O notation. So we can look at the reason of why OS squared is equals to 10 multiplied by n squared. So the reason is because this, okay, I know that the coefficient of this is 10, then I 1 up it, I make m to become 11. So it means that this time 11x squared will always be larger than 10x squared. So that is the part that I change my coefficient so that I fit yours by making a little bit larger than you, so that I can satisfy the condition that I'm always larger than you. So for this case, we have this part is equal to this part. So why is this the case? Because you notice that we can set m to be this number. So this is then 100,000. So this is 100,000 divided by 100. This will become 1,000. So 1,000 x squared will always be larger than 100 x squared. And in fact, this m coefficient, we can choose ourselves. We can make this to be as large as we want. We can make this to be 2 to the power of 1,000. That is fine. So yeah. Okay, so far everything okay? Any questions? Okay. Okay, then I'll move on to the next part. Which is the proving of this. Okay. So just now we manipulate our m, right? We manipulate our m so that we can fix the coefficient. Now we illustrate the example of manipulating x. Sorry, this should be 1 billion. I write this incorrectly. This should be 1 billion. To illustrate the example of ignoring the smaller coefficients. So if I let my n to be 10 to the power of 9, then this condition will always hold when x is larger than this number, because these two parts will become so insignificant that okay, this should be 2, this should be 2, m should be 2, sorry, this should be 2, this should be 2x squared. So the part behind will be so insignificant that it doesn't really affect anything already. So that is the one of the example that I manipulate the n. So now look at this. Why is it that the constant of 10 billion is equals to 1? Because we can always set the coefficient of this to just be 1, and then n, sorry, this should also become 10 billion. And then this will always hold. So an example that we can get is that, yeah, okay, so that's the example for big O notation. Now we want to prove some counter we want to prove something else. We want to say that, so suppose so my question is, we can never have ON plus C is equal to n squared. So why is this the case? So when we say ON plus C is equal to n squared, what we want is that we want let's say if we can, let's say if this is true. So suppose if this is true, then what we basically say is that we have an m, big M. When we multiply by n plus c, this will always be larger than n squared. So if this is true, then we have this condition. But what I am claiming now is that this will never be true. So the reason is we can use limit to explain this. Yeah, but I will not go into the details. If you're interested to look at, if you know how limit works, then you know why this is true. But basically, another way to think about it is that the largest term of this is not n squared, it's just n, so it can never become n squared. So the largest term of this is just n. So this can never become n squared. But the formal proof of why this is true is you can prove it using limit. So a lemma that we can get is that for any polynomial function fn, basically fn is equals to nd plus equals to a nd, a1 nd, a2 nd minus 1, and so on. So d is the degree, where d is the largest degree. We always have OFN is equals to nd. The reason, because we take out this coefficient, and then we only look at the largest term. We only look at the largest term. We ignore all the coefficients. So OFN is equals to n. Okay, and then yeah, but big O notation is not always tight. For example, if I write fn is let's say if fn is equals to n, I can write like this, right? But it can also be written as fn is equals to O n to the power of 100. Because what I am doing is just I'm looking at the upper bound. So like for example, like I'm just looking at the upper bound. So I can make my degree to be as large as possible. Or so that will still make my condition to be true. Okay. So far any questions? So why is this true, right? You sort of have to look back at the definition of this, which is that we want this condition to be satisfied. And then if gx is n, can already satisfy this condition, then if of course I can write this will become n multiplied with some hx, where hx is equals to n to the 1000. Because this is an upper bound relation. So 1 is always, let's say 1 is smaller than 10, I can always write this to be smaller than 1000. And this is smaller than 1 to 10 to the power of 9, 1 billion. So I can always increase my degree to be as large as I want, and the big O notation still holds, because it is an approximate upper bound. So, but it doesn't really make sense to like it's not useful, right? So if you say this, right, then what you're saying is that for all polynomial functions, right, I can always large the degree to be as large as I want. But this doesn't tells us what tells us. Remember, our intuition or our motivation of getting this is we want to get an approximation. We want to get an approximation of Fn, which is n squared. So I can say that n cube, but it doesn't really bring out the meaning of the original functions. So we want this to be as low as possible. We want the degree to be as low as possible, right? We don't want it to be so high that it lost its original meaning. So in some sense, you can sort of refer big O notation, or it is also commonly known as worst case, because it upper bounds the function. It is the worst case for the function. What is the yeah? So we all, like you look back at this bubble sort, for example. Sometimes it ends early and sometimes it ends late. So now we only look at the worst case. What happens in the worst scenario, and we just upper bound with on that. So we don't have to care about the early terminations and so on. We don't have to care whether it has run break or not, or whether it maybe it didn't swap. We just have to look at the worst case. So the worst case, because we are doing upper bound, so it sort of implies worst case. And big O notation capture the worst case with this inequality. But we can similarly define other notations. Like for example, we can define big omega notation, where big omega notation is just the best case. So look at this, right? So originally in big O notation, we have big O notation, we have fx is this. But then now we reverse the direction. We reverse to be lower bound. So if we reverse to lower bound, we are saying that the best case of your algorithm that you can run. So it's like saying that how fast can your algorithm run in the best scenario. So if you want to describe that, right, then we use big omega notation, which is this thing. And sometimes it could be possible that the best case and the worst case run at the same time. So if both bound are satisfied, then we use this big theta notation, which is basically says that in the best case, you probably gonna take, like for example, if Fn is equals to n squared, then in the best case, it will take around n squared times to run. And in the worst case, it will also take around n squared times to run. So basically, if theta gx is equal to fx, then we have fx is equals to omega gx, which is this part of the bound, and OGX, big OGX, and then big omega GX, which is the lower part of the bound. So the upper part and the lower part. So sometimes if we see theta, right, then we can just think of it as a tight bound. Because, yeah. Okay, so a quick example. So maybe a quick question on this. So now let's look at this. So what is the big O notation of this function or this program? Any guesses? Yep, it is n. The easiest way to look at it is because we already have the cow function fn. So big O of fn is equals to n. So that's the easiest way to think about it. But maybe a more interesting one, what is the big omega notation of this? Yep. The answer is Yihan got it right. The answer is still big omega is still n, because no matter what your input is, right, you will always run for n times, right? No matter what your inputs is, you always you always upper bounded lower bounded by n times. So the big so we can write this as theta of this function is equals to n. So now let's look at this function instead. What is the big O notation? And what is the big omega notation? Yes, you're right. Big O is still n. Because in the worst case, we have to run this part, which is n plus 2. So consider the worst case. The worst case, the input is when it goes into this path. So it will run this program for n time, this line for n time. So the worst case is still n. But what is the big omega now? Yeah, omega is 1, right? Because the best case is that we skip this part and then we just go directly to here. And that will only have 3 instructions. So this is the big omega notation. So for this function, we have that omega of fn is equals to 1, O of fn is equals to n. Then, so because of this scenario, we cannot write theta fn. We cannot write theta of fn because the upper bound and the lower bound is not the same. So we cannot write theta fn. So this is, we cannot write this down. It is not defined. Okay, any questions? Lemon Pool, do you have any doubts so far? Like which part? If you're not so clear of, you can ask now. Okay, nice. Okay, can I move on now? Okay, yeah, great. So right, so now let's analyze the running time for bubble sort. This is our final exercise for the day. How do we do it? So for bubble sort, what is the worst case? Big O notation, not the worst case, sorry. Big O notation and the big omega notation. So hint, right? The worst case that this could so if this is the worst, right, then what happens is that we sort of want the swapping to always across, and then we don't want this line to happen. We don't want it to be break. So the breaking condition here, the breaking from the loop condition is because it has already sorted. So because we no swap has been performed at all, so it means that it has already sorted. So in that case, we will break out from the loop, and then we will end early. But we don't want that to happen because we are trying to analyze what is the worst scenario that we can have to have as much running time, as much lines of instructions that is being run as much as possible. So what is the big O notation and big omega notation for bubble sort? Yep, big O is n square. You are right, because how do we look at this kind of questions, right? When we want to analyze the worst case, we just ignore, okay, we don't want this to, let's say if we don't want this, we want this break to not happen, right? Then we just ignore this. We suppose that this break does not happen. And then you look at this is a double nested for loop. So it should have, and then you have a loop from 0 to n minus 1 plus 1. So this will be some scenario of 1 plus 2 plus 3 all the way plus until n minus 1. So just now we know that this is equals to n times n minus 1 divided by 2, which is n squared minus n divided by 2. So we ignore the coefficients, then the big O of this will be n squared. So let's say if the break, the part of the breaking function did not miraculously did not happen, then this whole, it will only run the parts without break, and then at most, right, at most this will run for this many times, which is big O n squared. But now what is the perfect scenario? What is the best case? Yes, the best case is n. Why is it n? Because suppose that the array is already sorted, right? If the array is already sorted, then one pass of this will be done because we break out from the loop already. If the array is already sorted, then this swap will never be changed to true, and then it will break. So for bubble sort, we have O of n squared, omega of n. Okay. Any questions? Okay, nice, great. So in practice, right, how do we quickly know whether quickly find out the big O notation of a function? We just see how many nested for loop it has. If it has like 3 nested for loop, then it's n cubed. If it has like 4 nested for loop, then it's n to the power of 4. But of course, this cannot always be the case, because sometimes, let's say if you put a while true, and then if you have some condition, then you break, like, then sometimes it's a little bit harder for you to analyze. But a general way, like a very naive, easy way to look at it is you see how many nested for loop there is. If there, the number of nested for loop correspond to the n to the power of that number. Okay, so yeah, the algorithm runs in OS square, and best case is omega n. So actually, yeah, this part is wrong. I don't know why I put this. Yeah, just ignore this example. Okay, so now I finish on the difficult part. Now it's just on interpretation of asymptotic complexity. Okay, so we know our processor have this gigahertz thing, right? So the gigahertz somewhat correspond to number of instructions a processor can run in a second. Somewhat correspond to that. It is not always true, but on average, you can think of it like that. So 1 gigahertz basically means 10 to the power of 9 instructions that can be run in a second. So if you have 4 gigahertz, it means 4 to the power of 9. So 4 multiplied by 10 to the power of 9 instructions that can be run in 1 second. So therefore, if your algorithm has a runtime of O(n) cubed, you can expect it to finish within a second if n is equal to 1000, because 1000 to the power of 1000 to the power of 3 is equal to 10 to the power of 9, which is somewhat 1 billion. And then, because in a perfect scenario, your algorithm should be able to finish in a second. However, if n is 10 to the power of 5, then n cubed will be 10 to the power of 15. So now we divide 10 to the power of 15 by 10 to the power of 9. Then basically this says how many seconds requires to run this program, which is 10 to the power of 6 seconds. So 10 to the power of 6 seconds is somewhat around 11 days. So we can sort of imagine that n cubed, if you have an algorithm that is n cubed, then you try to fit some something some n 10 to the power of 5. Let's say if you are trying to do 3 nested for loop, and then your n is equals to 10 to the power of 5, this will finish the run in 11 days. Of course, it is just an approximation, but somewhat this is correct. So right now, let's look at some of the algorithms that we have and see their runtime. So we know sorting algorithm, the best sorting algorithm, comparison sorting algorithm that we have is the quicksort, which have expected running time of n log n. So if you want to sort 10 to the power of 10 to the power of 7 elements, it is still manageable within 1 second. You can just plug the values inside. The log right here is base 2. So you can put it inside a calculator, and then you see what is the value of that, and then you divide by 10 to the power of 9. That will be the number of seconds it requires for you to run approximately. And then the best known matrix multiplication algorithm is Stratton algorithm. It requires n to the power of 2.807 and so on. So it's a very complicated algorithm, but the best known approximately is this. So if your matrix, right, is dimension 10 to the power of 5, and you try to multiply these two matrices together, don't expect it to finish within 1 day. It will finish in 11 days. Okay. Okay, and then now let's look at factoring. Okay, the best known factoring algorithm for factoring a number for general field-safe algorithm is this very complicated expression. But it basically says, so you have the exp here. Exp is e to the power of x. E is the natural log, which is start with 2.7 something something. So let's just put 2.7. 2.7, and then you put all these things together, and then you calculate this. So I can say that this is a very slow function. If your n is very large, then this will run very slowly. You can just like put it inside the calculator to run it to run it yourself, and then get a approximation of how large your n is, for you to be able to how small your n is or how large your n is, then the expected number of time that is required for you to finish the algorithm. And yeah, so basically this run very slowly. And then we also have this another example, which is to compute the power of numbers modulo xd to a mod n. So this is just a very common algorithm that we always use to calculate something to the power of something, x to the power of d. And the claim here is that it only requires log d time or log d time. Why is this the case? So you look at the algorithm here, you realize that, okay, so this exponent is the d, and then during each loop, right, exponent will be divided by 2. So like, for example, after the first iteration, it will become d divided by 2, and then it will become d divided by 4, and becomes d divided by 8. So when exponent divides until it becomes 0, then this algorithm stops. So now we want to calculate how many times has this block been run. So we want to find d divided by 2 to the what? I put a question mark, such that this will become 0. And maybe we can look at a simpler example, which is this is equals to 1. If this is equals to 1, then we have d is equals to 2 of this, right? And then your mathematics just tells you that this is actually log to the base t and 2. That's why we have a log here, because we keep dividing by something. And if we keep dividing by something, then the log factor will come out. Okay, so right. So the last thing that I want to say is this part. Okay, let me just put this aside. Okay, so the last part that I want to say is this. We always, in crypto system, right, we always say that, oh, this thing has 128-bit security, 164-bit security, 256-bit security. What does it mean actually? So the bit security sort of means that the best algorithm currently available to break the scheme needs at least 2 to the power of 128 number of instructions. And you can try to convert, you try to divide 2 to the power of 128 by 10 to the power of 9. You see that this is a very, very large number, and it requires a long time to actually to break the scheme. So the larger your bit security, the longer time it requires for you to break the security. And this bit security directly somewhat directly correspond to the number of instructions that you need to run to the best algorithm out there. Okay, so yeah, this is a very fun thing to note. So we have this following order of asymptotic complexity. O1 is somewhat the fastest one, and then we have log n to the power of d, on to the power of d, and then O2 to the power of n, and n to the power of factorial. So notice that if you have an algorithm that runs in O2 to the power of n, then if your n is around 30, then you can run it within a second. Around that, sorry. Yeah, around within a second. 2 to the power of 30 is around a billion, something like that. But if n is equals to 60, don't expect it to run it to finish in any time. You just divide it by yourself. Okay, so yeah, this is just a very fun thing to note. So the slowest one is n factorial, which is basically means 1 multiplied by 2 multiplied by 3 all the way until n. Or I think there's one more, which is n to the power of n. Some algorithm actually runs in n to the power of n, but yeah. Okay, so yeah, I don't really have much time left, so that concludes my sharing for today. Any questions before we end it? Next week I will talk about Euclidean algorithm. So yeah, the main reason why I talk about this is because you sort of need a basic understanding of complexity to know why these algorithms, this fast algorithm matters. So that's the reason that I introduced this, and I believe it will also be useful for you all to know it. Like if you try to run a brute force algorithm that has 2 to the power of n, you can just don't try it. Like it won't end. Like it's just not possible to solve it using that. Okay, so any questions? Big O, no, big O for recursive function. Okay, that's a very interesting question. You have to analyze it. So different recursive function have different runtime complexity. So in our exam when we take like algorithm classes in NUS, one of the very common questions is they give you a function and they will ask you, like for example, they give you this thing, and then they ask you what is the time complexity of this. So what is the big O notation for this? But you still have to do a little bit of analysis yourself, and there is no really a automated way to do it. And for certain scenario, you can't even know whether your analysis is correct or not. Like you don't even know whether this is the best approximation that we get. So recursive function also different recursive function has different complexity. For example, merge sort and quick sort, you can define it recursively, and then it runs in n log n. And factorial, you can also define it in not factorial. Fibonacci sequence, you can also define it in recursive function. So yeah, you have to analyze it yourself. So in case you all didn't see it, I have pinned the notes in the Overleaf website. So you should be able to see the notes there and download it. Yeah, in some cases it will be n to the power of n, but not always true. So we have I'm not sure if you have heard of the problem of like yeah, never mind. Yeah, so complexity is a very interesting topic. You can work with it your whole life, and you still have things to do. So you can look at the Wikipedia page for like big O notations. They have a very thorough explanations of all the things that is going on. Okay. Any further questions? Okay. I guess no one has a question. Then I will end my talk here today. So next week we'll talk about Euclidean algorithms and analyze this thing. And also, I think we can also talk about modular operations. Then finally, we can talk about RSA. This is just a build up for RSA. If you remember, the title is number theory for RSA. Okay, so